There are plenty of easy ways to figure out how much area there is under a curve for a linear, absolute value, or horizontal line. However, when the line isn't perfectly straight, like a quadratic, exponential, or hyperbola, it is much harder to find the exact value for the area underneath. This is where sigma notation comes in the form of left endpoint rectangles, right endpoint rectangles, and trapezoids.
Let's say that you have a downward-facing parabola y equals negative 0.5x minus 1 squared plus 8, and you want to estimate the area underneath the curve between x equals 1 and x equals 4 in 6 rectangles. To get an overt estimate of the area, you use left endpoint rectangles. Starting with the value x equals 1, draw a straight line up until it intersects the line at y equals 8. Then, to make the rectangle, draw a horizontal line until you get to 1.5. Then, since you have 6 rectangles, move to x equals 1.5 and draw a line up until it hits the line, same as before. Continue this until you have 6 rectangles, the last one up from x equals 3.5. When you find the area of all these rectangles by multiplying delta x by the height where it intersects with the line, and adding the total area, it should be an overestimate of the area, because as you can see, the top right corners of the rectangles end up over the graph. We have the exponential graph y equals 2 to the x minus 2 plus 3, and we want to estimate the area under the curve between x equals 0 and x equals 3. Since this has a positive slope, right endpoints rectangles will give you an overestimate. You want to separate delta x into 5 rectangles, making each rectangle 0.6 units wide. Starting at x equals 0.6, draw a vertical line up to the curve, then once you reach the line, draw a horizontal line left to x equals 0, making a rectangle. Continue this for all x values that increase by 0.6, drawing the last line up from x equals 3. Now you have 5 right endpoint rectangles. When you calculate the area of all the rectangles combined, just like you did in the last problem, the answer will be an overestimate.
The third way to estimate the area under the curve is to use trapezoids. This is a more accurate way to measure the area under the curve because they are an average of right and left endpoint rectangles. When using piecewise functions that contain absolute values, linear lines, and horizontal lines, trapezoids are especially useful. Imagine you are in a running challenge competing to see how much distance you can cover in an hour. For the first 30 minutes, you run at a consistent pace of 5 miles an hour. Then for the next 20 minutes, you steadily increase your pace until it reaches 10 miles an hour. Then for the remaining 10 minutes, you remain at your pace at 10 miles an hour. So how much distance did you cover? We graph this on a velocity time graph because velocity times time is equal to distance. The middle 20 minutes of your challenge, when there is a steady linear increase from 5 miles an hour to 10 miles an hour, is where we will use the trapezoid. The formula for a trapezoid laying on its side is 1/2 of base 1 plus base 2 times height. But due to its new orientation, the height becomes the base, and the base 1 and base 2 become the lengths of left and right endpoint rectangles. The final equation is 1/2 times 1/3 times 15, which is equal to 2.5, and the total distance ran is 6.7 miles. Differences. What are the differences between right endpoint rectangles, left endpoint rectangles, and trapezoids? On any graph, one type of rectangle will be an overestimate and the other will be an underestimate, and a trapezoid is always the average of the left and right endpoint rectangles. On an upward-facing parabola to the right of the vertex, left endpoint rectangles will always be an underestimate, while right endpoint rectangles will always be an overestimate. If you average them, you would get the area you would have gotten using trapezoids. For example, let A equal the sum of the areas of the left endpoint rectangles, and let B equal the sum of the areas of the right endpoint rectangles, and let C equal the sum of the areas of the trapezoids. With this, A plus B divided by 2 is equal to C. Another way of looking